Hello everybody, Big Bang and stock market. You see, my friends, I love cosmology. I love cosmology a lot. When I was a kid, I read a lot of books about cosmology. Actually, at that moment, cosmology it's not accepted as science. It was kind of they consider it as something between physics, astronomy, and fair stories. Later, when I was a student, and now I reading books about cosmology, reading articles, watching videos. I love cosmology, and I'm happy that last weeks I have found one technology in timing solution where I have applied math close to math used in building one astronomical model, one cosmological model, Big Bang model. You see the main persons here, they are just sec. This is left, this is greatest American astronomer Edwin Powell, greatest guy, and Belgian physicist and priest, by the way, Georges Lemaitre. They discovered, they discovered a law. It's called Hubble-Lemaître law. It states this: galaxies are moving away from Earth at speed proportional to the distance. In other words, the farther a galaxy is from the Earth, the faster it moves away. How it happens? Actually, George Lemaitre discovered this phenomena in 1927, and in 1928, several months before Great Depression, Edward Hubble published his articles. He worked at the biggest telescope at that time, 100-inch telescope in Mount Wilson, and he published this table, this chart. This is famous chart. He analyzed distant galaxies located far away from our Milky Way galaxy. And he analyzed 24 galaxies, and X here represent the distance between for these galaxies. How far these galaxies located from Earth. At that moment, they have found the way how to calculate this distance. And y-axis, it represents a redshift. It represents how fast these galaxies move away from us. For example, if galaxy located 20 megaparsec from us, this galaxy move away from us with speed about 1500 kilometers per second. 1500 kilometers per second. By the way, parsec, this is huge distance. Actually, 1 parsec. This is distance to closest to us star, to Earth star. This is Proxima Centauri star, and light travels 3.3 years to reach this star. And here, distance to closest to galaxies, millions parsecs. It's much more further. And you see this is Hubble constant. So how increasing the speed, it's 68 shows kilometer per second for one megaparsec. Actually, there are for other sources, other experiments, they suggest another value for Hubble constant, 72 kilometers per second for 1 megaparsec. It's so far it's unclear why it happens. It's so called Hubble tension. So how Hubble calculated the speed, how fast galaxies move away from us? I would like to explain you more detailed because we will use this phenomenon in timing solution. He actually calculated the spectrum for galaxies. Spectrum, I mean chemical spectrum. You see, if we watch some element, watch through spectrogram, this special device, you see this is colored chart and colored stripes, and you see there are vertical line. You see black vertical line. This is emission lines, and each chemical element has his own set of chemical lines. For example, this line, as I know, this is one of line hydrogen line, and I guess mostly this line used because hydrogen element is most common element for in distant space. And so when Edward Hubble got spectrum for distant galaxy, he has found that these lines, you see these emission lines, black lines, shifted to red zones. Red shifted to these red zones. It means that light is stretching. The length of light is getting bigger. It means that this object moves away from us. This is red shift. If this object moves toward to us, getting close to us, it would be blue shift. These lines shifted to these zones. This is blue shift. Now I would like to show you how a red and blue shifted wave work in tiny solution. You see, it was developed recently, a very interesting model, wavelet analysis, but here we applied very special algorithm. We calculated wavelet using Q-spectrum, using walk-forward analysis. And you see these horizontal lines, red lines, represent the most important cycles. Like these cycles, it's how many? 600 days cycle. And you see sometimes the period of this cycle changes. For example, you see this vertical line, horizontal line, the period changes. And here we can draw cycles with changeable period. Click here and drag a mouse cursor from here to here. Here, and you see program shows that the period of this cycle, maybe we'll put here more. The period of the cycle changes. Here, this period was 471 days, and here at that moment we have 400, almost 500 days cycle. And you see the period of the cycle increasing. And I will do this. I will increase this value. Just show you just an example how it works. And you see the period of the cycle. You see period changes. This is stretching wave. This is a red shifted wave. It means that period of this cycle is increasing, and program indicates that this cycle is red shifted here. And I will show you another example, blue shifted wave. You see I move this anchor to here, so the period of the cycle changes. At that moment it was 471 days, and at that moment the period of the cycle 269 days. 269 days, and you see this stripe blue. It means that blue shifted cycle, and you see the period of this cycle decreasing. This is squeezing wave. Red, we have a stretching wave, like in a Hubble experiment, and this is squeezing wave, or contracting wave. This is blue shifted wave. And now let's back to 1929. Edward Hubble just published his results about redshift phenomena. and outside is Great Depression, stock market crashes, but in science many important things happens. You see, before that, in 1915, Albert Einstein published his general relativity equation. They call it Einstein field equation. It looks this way, but it's much more complicated. This is actually tensor equation. It's much more complicated than it looks. And you see, actually, it was a question: what kind of universe we live? Because you see, this equation, it has found that this equation is not stationary equation. It means that maybe we live in expanding universe. So the space is expanding, it's stretching. Or in other variants, we live in contracting universe. The universe is contracting. It depends on matter density in our universe. Actually, Albert Einstein did not like non-stationary equation, and he added special lambda cosmological to make this equation stationary. But everything changed. Then Edward Hubble published his results. It has found that our universe is actually non-stable and it's expanding. We live in expanding universe. If universe is expanding, this is actually cosmological phenomena. If we live in expanding universe, it should be some moment, Big Bang, when everything will be collected in one point. Some Big Bang phenomena that took place 13.9 billion years ago. As an example, if our universe would be contracting, it would be a big crunch phenomena, but it in future. But in reality, it looks like we live in expanding universe. Now, I will explain how we can apply this knowledge for forecast stock market. You see, in time and solution now with new Wavelet model, we have possibility track the cycles with changeable period. And the most important thing you need to understand about these cycles with changeable period, that this cycle works not as a regular cycle works. You see, these cycles you need to take care about singularity. You see here two examples. This is a red shifted wave. Calculated with time in solution Wavelet model. You see the period of this cycle increasing, and it means that there is some point in past when this period equal 0, like Big Bang. Exactly. So if we working with red shifted cycle increasing period, we have some singularity point in the past. And another example, this is a cycle blue shifted cycle. This is cycles with decreasing period, and there is point in future when this period is 0, big crunch. So you need to take care, working with changeable cycles with changeable period. You need to take care singularity points, dates when period of analyzed cycle equals 0. And now I will show you how to work with cycles with changeable periods. You see, this is a new feature in time in solution new Wavelet model. Actually, this is absolutely new for me. This model has been developed about 2 months ago, and now I know users use this model a lot. And what is new there? The new is this model allows to see how cycles change, how the period of cycles changes. Before that, it was absolutely impossible to do this. Classical spectrum does not allow it, doesn't matter what algorithm we use. Classical wavelet analysis based on Marlet transform does not allow allowed to do this as well, but new Wavelet model does that. I will show you example. You see, I have downloaded already Dow Jones since 1789 monthly data, longest available Dow Jones, and calculated Wavelet, new Wavelet to see working economical cycles here. You see, this horizontal stripe represent cycles. You see these red lines. And interesting fact that we can see that these lines are inclined. You see, this is, for example, this is 10-year cycle. This is definitely jugular economical cycle. We know that this cycle works for Dow Jones. Now the period of this cycle is about 10.35 years. And for example, 100 years ago, the period of this cycle, it was, I tell you, 8.79 years. So it was almost 2 years shorter, 100 years. And in 1870s, the period of the cycle was less than 8 years. You see this line, the period of the cycle changes. This is absolutely new feature. Classical spectrum does not allow to see this phenomena. Classical wavelet analysis, if I switch to classical wavelet analysis, just a sec, you see, we see nothing here. It's very difficult to find. But algorithm-based wavelet based on Q-spectrum algorithm allows to see cycles very, very precisely. Just a sec. And the new feature here, this module allows to build cycles with changeable period. We need to click this button. Here I click cycles with fixed period, and this is cycles with changeable period. And simply drag mouse cursor from here to here. You see this line inclined. So we have a line. You see this line covers this horizontal, this stripe, red stripe. And you see you can use actually this option, just a sec. You can use this option, optimize the cycle. Just a sec. You can click this button and program will optimize this cycle. The program will find the best parameter for this cycle with changeable period. You see, it has found that here and 1880 something, the period of the cycle was 8.26 years, while now it's 10.3 years. It's 2 years longer. And here we can see how the cycle works in time. So this is cycle with changeable period, and we can see how the cycle works. And for example, another cycle, kitchen inventory cycle. Kitchen inventory cycle, this, you see this stripe. This stripe, actually I can drag, display this piece of wavelet, just a sec, and you see this cycle is here. Cycle is period 40 months. I drag mouse cursor to cover this this cycle, and now I click optimization to find the best parameters for this cycle. And program has found that in end of 30 years ago, the period of the cycle was 40.89 months, while now it's almost 2 months longer, 2.64 months. This is kitchen inventory cycle with changeable period, and here we can see how the cycle works in time. So this is new feature that allows to see cycles with changeable period. And now I will explain you the parameters of changeable cycles. You see, first it shows first period. The period at the beginning, it's 8.25 29, 26 years. And this is another parameter. This is period now. So now the period of the cycle is 10 something years. And there is one more parameter, we call it Z. This is the idea pretty much the same as cosmological Z they used to measure distance for very distant objects. This is factor Z factor. It shows how fast the period of cycle increasing or decreasing. This is within one period. Cycles period increasing on 1.4% in this case. And one more option, just a sec. You see this. You see this is a red stripe, horizontal stripe. It means that this cycle is red shifted. It means that this cycle, the period of this cycle increasing, and the period increasing with speed 1.4% within one period. What I have found, you see, it looks like usually the period does not change much. Usually Z about 1.5, this is most typical value for speed of cycle changes. Usually less than 5. So cycles changes, but they change not so much. It means that the singularity points located very far from our data. But you can see this singularity point making here check timeline, and the program will show how the period of this cycle changes in time. Just a sec, it's calculating. You see this line, this green line, it shows how the period of the line changed, and singularity points located in 14th century, 13, 18 years. So it's located very far away from our data. So we can simply ignore this singularity. But there is special case, then something work different way. The case is, you see, there is one phenomena in Wavelet model that I call it distortion area enigma. You see, this is very experimental. I absolutely have no idea how it works this way, but look at this. When I calculated Wavelet, new Wavelet model, I was did not understand what is going on here. Why this area, you see, look at this line, there is kind of distortion. It's like smashed line. Something I thought that maybe it's some side effect. I changed this target, but not this distortion presents. Maybe this is some new phenomena, and there is one idea. Let's do this. I will emphasize this this area, this part of wavelet chart. And now I draw a wavelet chart, a regular cycle from here. The distortion area goes this way and somewhere here. Yeah, okay, I do it this way. Okay, no, it's somewhere here. Oh. No, it's here. You see, this is, I draw this cycle based on this distortion area. There you see, and the period of this cycle, you see, changes a lot. It's in 1940 something, 45. The period was 47 months. It was a 4-year cycle. But now the period of this cycle, it's 24 years. Now the periods of this cycle much more longer. But the most interesting fact, look at this date. this date indicates that singularity points its beginning of 1930s. Maybe this is a Great Depression. Maybe singularity point for this distortion area, this is Great Depression. And this Great Depression developed a special wave that at that moment, 1930s, it was a very short cycle with short period. The period of the cycle was 26 months, as you see. But now the cycle increasing. This is a redshifted cycle, and now the period of this cycle 24 years. And we can see how this cycle works now, but 1930s it worked this way. You see, this is great. It starts here, and you see, and the period of the cycle increasing. So this is some new phenomena. I don't quite understand how it works this way, but you see, it shows changeable cycle, indicates that this point, Great Depression, looks like this is singularity data. This is kind of Big Bang for cycles. That this phenomena, burn cycle, that now it's period of this cycle 24 years. It's very interesting. Now resume. Firstly, we have tool that allows to work with regular cycles with changeable period. You simply draw the cycle using Wavelet model and verify a standard wave. And second, it looks like distortion areas opens us doors to singularity phenomena, singularity cycles. This is very interesting phenomena. This is very experimental feature, and you see singularity looks this way. Cycle, that period of the cycle in 30s, it was 1 year, even small period. Now the period of this cycle, it's 24 years. So this is a cycle in Great Depression, started cycle that started with period less than 1 year, and now this period 24 years, kind of Big Bang, looks like Big Bang. So this is absolutely new techniques. So that's it. Thank you.